the global defense industrial base is facing a critical vulnerability in its chemical supply chain. Antimony, a metalloid essential for military-grade flame retardants and precision munitions, is highly concentrated in hostile jurisdictions. As shown in the primary mine production data, China consistently controls over half of global extraction, averaging 81,200 metric tons annually. Meanwhile, the United States has recorded zero domestic primary mining capacity since 2001. This leaves Western defense contractors entirely dependent on foreign imports for raw stibnite concentrates. Even alternative suppliers like Tajikistan, which produced 16.1% of global output in 2023, rely on Chinese networks for final smelting. Geopolitical leverage has now translated into acute market friction. Following China's export restrictions in August 2024, spot prices for antimony metal surged by 140%. Prices escalated from $12,100 per metric ton to historic highs exceeding $25,100. This price shock directly correlates with a widening structural deficit in the West, which reached 12,000 metric tons in 2024. The shortage directly impacts the production of military-grade antimony trioxide. This compound represents 35% of defense consumption and is vital for combat vehicle and aerospace survivability. This supply crisis is not unprecedented, but the modern capacity to respond is fundamentally constrained. In 1940, the United States bypassed regulatory hurdles to bring the Yellow Pine mine online in under 12 months, securing 90% of Allied antimony. Today, the domestic stibnite gold project in Idaho faces a capital expenditure of $1.26 billion to spend over 12 years in environmental review under the National Environmental Policy Act. While the project is projected to eventually supply 11,500 metric tons annually, it cannot resolve the immediate 36-month defense deficit. The divergence highlights how regulatory and capital friction prevent rapid industrial decoupling in high-technology defense sectors. The Western defense industrial base is constrained by a critical single point of failure in solid rocket motor production. A single facility in Cedar City, Utah, synthesizes over 95% of the aerospace-grade ammonium perchlorate for the Western Hemisphere. This chemical oxidizer is the primary mass component in tactical and strategic missile propellants. As shown by the capacity threshold, domestic production is capped at 9,000 metric tons annually. Projected demand crossed the ceiling in late 2022, creating a structural deficit that will reach 3,100 metric tons by 2026. This deficit is driven by aggressive procurement ramps for precision munitions and air defense interceptors. Guided multiple launch rocket system production is scaling to 14,000 units annually by 2025. Concurrently, Patriot interceptor manufacturing is ramping to 650 units per year. The physical mass requirements of these systems reveal the scale of the chemical bottleneck. A single rocket motor requires approximately 100 kilograms of solid propellant, 70% of which is ammonium perchlorate. At peak output, this single program consumes nearly 1,000 metric tons of the chemical annually. Solving this bottleneck is constrained by the physics of chemical synthesis, not just capital availability. Establishing a redundant domestic production line requires an estimated $150 million. However, the lead times are highly inelastic. Constructing the specialized electrolysis cells for sodium chlorate conversion takes 36 months, while environmental permitting adds an 18-month regulatory delay. This structural friction mirrors the early Cold War propellant crisis of 1954 to 1957. Rapid solid-fueled missile development then outpaced chemical processing capacity, forcing direct state intervention to underwrite redundant industrial plants. The scaling of artificial intelligence accelerators is fundamentally constrained by the physical limits of advanced packaging. High-bandwidth memory relies on vertically stacking dynamic random access memory dies connected by microscopic copper channels. As stack heights increase to meet bandwidth demands, cumulative packaging yields decline exponentially. Compounding defect mathematics dictate that a single failure in any vertical channel ruins the entire multi-die stack. For current 12-high HBM3E configurations, packaging yields hover between 50 and 55%. This low efficiency effectively doubles the raw silicon wafer consumption required for each functional memory module. By 2026, the projected transition to 16-high stacks drops estimated yields below 20%, threatening the economic viability of next-generation hardware. The primary physical bottleneck is the metallization of through-silicon vias via precision electroplating. As these vertical channels become narrower and deeper, uniform copper deposition becomes highly difficult. Beyond an 8:1 aspect ratio, copper ion diffusion rates fall below the deposition rate at the channel opening. This causes premature pinch-off, trapping the liquid electrolyte and leaving structural voids. To prevent these voids, manufacturers must slow the electroplating process, extending fill times from 12 minutes to 2 hours. This adjustment reduces plating tool throughput by 90%, paralyzing cleanroom output. At a 12:1 aspect ratio, the defect rate rises to 65 parts per million. Across a high-density memory stack containing over 10,000 connections, this defect rate guarantees module failure. These microscopic chemical defects translate directly into systemic macroeconomic friction. Cumulative industry losses from discarded silicon and packaging materials are projected to exceed $15.6 billion between 2023 and 2026. Because high-bandwidth memory requires 3 times the wafer area of standard memory, low packaging yields divert critical lithography capacity. This diversion inflates global server memory pricing across the entire enterprise computing sector. This packaging crisis mirrors the multi-chip module reliability failures of the late 1980s. Mainframe computer manufacturers then faced similar interconnect failures before standardizing ball grid array technology. Today, manufacturers are forced to divert capital expenditure toward advanced physical vapor deposition and specialized bonding equipment to bypass these physical limits. The International North-South Transport Corridor relies on a critical maritime link across the Caspian Sea. This link is failing due to a severe hydrological crisis. As shown on the dual-axis plot, the Caspian sea level declined by 1.85 meters between 2012 and 2024. This drop directly degraded the controlling depth of the Volga-Caspian Canal to a critical low of 3.10 meters. The canal now sits far below its 4.5-meter design draft, forcing vessels to light load. Siltation rates continue to outpace standard maintenance dredging. Physical draft constraints translate directly into severe microeconomic penalties for shipping operators. Reducing vessel draft from 4.5 to 3.5 meters cuts cargo capacity by 38%. This drops a standard Volga Max vessel from 5,000 to 3,100 deadweight tons. This capacity drop forces a 61.3% freight cost penalty per ton-mile to cover fixed operating costs. At the 2024 low water mark of 3.1 meters, capacity utilization falls to 46%, effectively doubling transport costs. Geopolitical demand for this sanction-resistant corridor is outpacing the physical capacity of its infrastructure. While actual transit volume reached 6.8 million metric tons in 2024, suppressed demand surged to 9.5 million tons. Russia scaled dredging operations by 200% to 10.5 million cubic meters, yet failed to restore the target draft. The gap between realized and potential trade has widened by 427% since 2018. This friction mirrors the late 19th century Mississippi River low-water crises, where severe draft limits paralyzed trade until massive engineering interventions occurred. The global transition to renewable energy grids is hitting a hard physical constraint in utility-scale energy storage. While policy mandates have doubled the planned pipeline for pumped storage hydropower, the industrial base required to manufacture the core turbomachinery has contracted by half. As shown by the supply-demand divergence, global planned capacity has reached 310 gigawatts in 2024. Concurrently, the number of qualified heavy foundries capable of casting the critical 100-ton stainless steel runners has fallen from 12 to 6. This industrial contraction has caused procurement lead times for reversible Francis pump turbines to surge from 24 months to 54 months. This bottleneck is defined by extreme geographical concentration. China commands 65% of global ultra-large runner casting capacity and operates 42 active multi-axis precision milling machines. In contrast, North American domestic capacity is limited to 25,000 tons annually, representing just 5% of the global total. The physical requirements for these components are highly demanding. A single unit requires a continuous pour of up to 150 tons of molten stainless steel to yield a finished 100-ton runner. Fewer than 10 facilities worldwide can execute this process, leaving Western grid decarbonization structurally dependent on foreign heavy industrial infrastructure. Deconstructing the procurement timeline reveals that the bottleneck is physical, not administrative. The casting and forging phase has expanded from 8 months in 2016 to 22 months in 2024. Total nominal procurement costs for a single turbine unit have escalated by over 100%, reaching $38.4 million. These delays are highly inelastic. The physical casting, cooling, and multi-axis machining steps have rigid thermodynamic and mechanical limits that capital injection alone cannot compress. This manufacturing deficit parallels the turbine shortages of the 1930s during the construction of the Tennessee Valley Authority. Then, as now, rapid infrastructure expansion was ultimately capped by the physical capacity of heavy industrial foundries. The electrochemical performance of electric vehicle batteries is governed by anode structural integrity. Synthetic graphite is highly favored for its superior cycle life and fast charging capabilities. However, transforming amorphous carbon into a crystalline lattice requires heating precursor materials to over 3,000 degrees Celsius. This process, known as graphitization, is highly energy intensive. As shown in the regional cost comparison, industrial electricity tariffs dictate the geography of anode manufacturing. In Inner Mongolia, cheap coal-fired power limits graphitization energy costs to just $160 per metric ton. In contrast, developers in the United States and Europe face power costs of $320 and $600 per metric ton, respectively. This creates a severe regional cost premium that renders non-subsidized Western projects uncompetitive. The economics of graphitization are highly sensitive to grid tariffs and furnace efficiency. A standard process efficiency of 4,000 kilowatt-hours per metric ton, every $10 increase in megawatt-hour rates adds $40 directly to the cash cost. Transitioning to state-of-the-art continuous systems can reduce energy consumption by 40%. Yet, even these efficiency gains cannot fully offset the structural disadvantage of high Western grid tariffs. The steep slope of legacy batch furnace lines illustrates why older Western facilities face immediate economic obsolescence. Without direct power subsidies, domestic projects cannot bridge the operational cost gap. This physical constraint creates a profound environmental paradox for the green energy transition. The high-performance synthetic graphite anodes required for Western electric vehicles are overwhelmingly manufactured using highly polluting coal-fired electricity. Global production capacity expanded from 370 kilotons in 2018 to an estimated 1,600 kilotons in 2024. China-based, coal-powered facilities accounted for over 78% of this growth. By 2026, China's coal-powered capacity is projected to reach 1,700 kilotons, emitting up to 37.4 million metric tons of carbon dioxide equivalent annually. Meanwhile, non-Chinese clean-powered capacity will reach only 160 kilotons. This leaves the Western supply chain deeply tethered to high-emission coal grids. This structural bottleneck is historically analogous to the early aluminum smelting industry. The Hall-Héroult process forced smelters to cluster exclusively around the earliest cheap hydroelectric sources, such as Niagara Falls and the rivers of Norway. Today, modern graphitization remains bound to regions that can offer uninterrupted, low-cost industrial power at scale. The maritime shipping industry is facing a severe mismatch between decarbonization mandates and physical fuel supply. Global orders for dual-fuel container vessels are scaling rapidly, with the active fleet projected to rise from 30 units in 2023 to 275 units by 2028. This vessel deployment is driving an exponential surge in fuel demand. By 2028, annualized demand for green methanol will reach 4.80 million metric tons. However, global production capacity for this fuel is projected to reach only 0.85 million metric tons. This leaves an 82.3% structural deficit, forcing operators to revert to conventional fossil fuels. This supply deficit is compounded by a lack of localized port infrastructure at critical maritime choke points. The Strait of Gibraltar, which handles over 100,000 vessel transits annually, remains locked into conventional hydrocarbons. By 2028, conventional fuel capacity at the strait will expand to 7.60 million metric tons. Meanwhile, green methanol bunkering capacity will reach only 0.12 million metric tons, or just 1.38% of the regional total. This infrastructure deficit is highly inelastic. Administrative, safety, and environmental permitting for new chemical storage terminals in Spain carries an average lead time of 5.5 years, preventing rapid capacity adjustments. Current friction mirrors the historical transition from coal to oil bunkering between 1910 and 1925. During that period, coal's share of global shipping tonnage declined from 96.4% to 64%, while oil rose to 36%. The rate-limiting step was not the development of internal combustion diesel engines, but the physical deployment of oil bunkering stations. Early oil cartels had to invest massive capital to challenge British coal station hegemony. Today, the green methanol transition faces an identical structural lag. While dual-fuel propulsion technology is mature, the physical deployment of global refueling networks is lagging by more than a decade. The Colorado River Basin is facing a structural crisis where hydrological decline intersects with soil salinization. As river volumes decrease due to drought and overallocation, the concentration of total dissolved solids rises. By 2024, average salinity at Imperial Dam reached 848 milligrams per liter. This leaves a narrow 3.5% buffer before violating the federal treaty limit of 879 milligrams per liter. This chemical shift carries severe economic consequences. Annual damages in the lower basin have scaled nonlinearly to $430 million. Quantitative models show that each single milligram per liter increase in salinity inflicts $340,000 in incremental damages. This damage manifests as accelerated pipe corrosion, industrial scaling, and reduced crop yields. The primary infrastructure designed to mitigate this salinity crisis has functionally failed. The Paradox Valley Unit in Colorado prevents natural brine from entering the river system by injecting it 16,000 feet underground. However, this process induces seismic activity. Following a 4.5 magnitude earthquake in 2019, operators curtailed injection by 70.5%, dropping annual salt interception to just 28,000 tons. Meanwhile, the Yuma desalting plant in Arizona has remained entirely non-operational. The reverse osmosis facility is kept in a standby maintenance mode that costs $30 million annually without removing any salt. This combined infrastructure deficit has allowed over 1.2 million metric tons of unmitigated salt to enter the river system over the last decade. This rising salinity directly threatens the agricultural viability of the Imperial Valley. High-value vegetable crops like onions and lettuce are highly sensitive to salt concentrations. At the current baseline of 750 milligrams per liter, onion yields drop by 10% and lettuce yields by 5%. Alfalfa, which covers 60% of the valley's irrigated land, suffers a steep 10% yield drop for every subsequent increase of 250 milligrams per liter. To prevent toxic salt accumulation in the soil, farmers must flush fields with 10 to 15% excess water. This practice, known as the leaching fraction, directly worsens the basin's severe water deficit. This ecological crisis is structurally similar to the salinization of ancient Mesopotamia. Without functional drainage and desalination infrastructure, continuous irrigation leads to a systemic decline in soil fertility.